Hi, let me get back in the picture here. Welcome back. Or maybe it's just me that's getting back. But today we're going to look at applications of FTC1. The first part of the fundamental theorem of calculus. To remind you, again, I mentioned this in the previous video, FTC1 says that if f is continuous on the closed interval AB, then g of x, which is the function from a to x of f of t dt, is continuous, differentiable, and g prime of x is equal to f of x. By the way, the domain, I should say, x is an element of the interval a to b. This is sometimes called the area function. If my function f is non-negative, then this actually represents the area. This is f of t. My function, well, let me just put f. And this is a to b. And if this function is non-negative as I drew it, then as x moves, we actually get the area under the curve from a to x. But this is valid even if my original function is not non-negative. In that case, it wouldn't be an area function, but still. Now, the important part, and we're not going to prove this, we'll just take it on faith. The important part is g prime of x is f of x. So, we want to look at some applications. If I have y equals, that's going to be my g, the integral from 2 to x of 3 sine t over t squared plus 1 dt. Notice here, by the way, before I go any further, the variable is in the upper limit. That is the variable for this function, not on the inside. Anyway, my derivative y prime according to FTC1 is just going to be 3 sine of x over x squared plus 1. You just take the variable and replace the dummy variable on the inside of the integrand. That's your derivative. That's all it is. Now, seems kind of simple. Let's look at some little bit more interesting examples. Suppose I have, I will erase this also. Suppose I have y equals the integral from x ln of x to 10 of tangent of t dt. Now, my FTC1, we need the variable to be in the upper limit, not the lower limit. So the first thing I'm going to do is reverse these, and there's a property of definite integrals that says that this is equal to the negative of the integral from 10 to x ln of x of tangent of t dt. Basic property, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. And now I can use, again, this is still the original function. Its derivative then, use FTC1, is going to be the tangent of x ln of x, but we're not done because I have to use chain rule times the derivative of x ln of x, which is first times the derivative of the second, plus the second times the derivative of the first. And so therefore I end up with the tangent of x ln of x times the quantity 1 plus ln of x. That would be the derivative. Let's suppose that I have This is 1D on the worked out solutions. The integral from 0 to arc sine of e to the negative x of t cubed times the natural log of 2t plus 1. Okay? And so my derivative, this is a function y equals, the derivative then is going to be, replace, I'm going to get the arc sine of e to the negative x, quantity cubed, times the natural log of 2 times the arc sine of e to the negative x plus 1. And then again, I have to multiply this by the derivative of my function that's in the upper limit. And mainly I did this to remind you what the derivatives of some of these things are. The derivative of arc sine would be times 1 over the square root of 1 minus x, 1 minus generally x squared, but in this case I have e to the negative x, quantity squared, which is e to the negative 2x, times the derivative of e to the negative x, which is negative e to the negative x. And I'm just going to leave this like this. It's kind of ugly.